What hurts the most? This is a question being investigated by many pain researchers and one we are here to help with. Hello, and thank you for joining our TechCast today. I'm Chris Rand from Aurora Scientific, and I have the pleasure of discussing how complex mechanical stimulation can be made simple with the 300C-I dual-mode indenter. As an overview, today I'll be talking about how the 300C-I works and the components that make it happen. You might be asking yourself, what can I measure or do with this type of equipment? With that in mind, I will cover experiments commonly performed, as well as how they are executed with the indenter. Dual mode gets its name from having two functional inputs and outputs that can control and measure force and length. When in length control, the system executes precise movement of the motor position while measuring resistive force. Alternatively, when in force control mode, the system applies a constant force or load while measuring the length required to reach that defined force. If the controller is the brain of the operations, then the servo motor operates as the hand. The ability to execute fast, reliable, and precise mechanical stimulation mainly lies with the motor. The servo motor can be operated in any spatial orientation to ensure the application area can be stimulated and that the area remains constant throughout. By mounting the motor to a manual stage or a motorized stage, you can minimize off-axis forces that are common in handheld applications. Keeping with our analogy, the motor or the hand can only provide low-level accuracy, but when you add the finger and fingertip, you get high-precision stimulus application. This is what the extension tube and tips provide. The extension tube can extend the application area away from the motor case and easily couple to the 3D printed indenter tips. A wide array of tip diameters can then be used to vary application area from 0.3 millimeters all the way up to 3 millimeters. A very common experiment or application for the mechanical stimulator is to assess mechanosensitivity, whether this be measuring sensitivity in the meninges of a rat model of migraine headaches, or nerve tongue preparation to study pain associated with oral cancer. Pain researchers can define mechanosensitivity into two main groups: allodynia, which is a pain response to a non-painful stimuli, and hyperalgesia, where the response to normal pain is increased. Another experiment that assesses sensitivity is a vibrotactile stimulation, which consists of a sinusoidal tactile stimulation of a surface such as the sole of a foot, palm of a hand, or other types of tissue. This test is designed to measure subject sensitivity or reflex response to varying stimulation frequencies, often in a diseased state. When you think about the field of somatosensation, something that frequently comes to mind is the concept of a receptive field. This is an area on the skin or tissue that is innervated by free nerve endings of a single nociceptor or mechanoreceptor that responds to mechanical stimuli. Generally, the smaller the receptive field, the greater location acuity is said to have. These can then be mapped out by varying the location of stimulus and recording the receptor activity in response. At this point, you may be thinking, okay, that's great and all, but how do you actually perform the mechanical stimulation required to measure mechanosensitivity, vibrotactile stimulation, or the size of a receptive field? In this section, I'll outline the experimental setups or types of protocols you can employ to generate this kind of data. First off, we will look at performing precise indentation by controlling the depth of mechanical stimuli. Here, we will command the motor to indent a defined distance over a set duration and then be released. You can then vary the depth of the stimulation to look at tissue sensitivity or material stiffness. As you can see in this side-by-side video, where we have our mechanical stimulator on the left and acquisition software on the right, we are executing mechanical stimulation at varying depths. In this case, 1 millimeter, 2 millimeters, and 4 millimeters, with the resultant force profile shown in the top right. On the left, you'll see the indenter arm with extension rod and tip push into the membrane, hold, and release at each predefined depth. Another experiment we can perform, which was alluded to earlier, is vibrotactile stimulation. In this setup, you can execute sinusoidal stimulation of a hand, foot, or other tissue at varying frequencies and amplitudes and measure the corresponding response from a subject, tissue, or receptor. When we look at the unit in action, we are running a series of sinusoids at just under 1 millimeter peak-to-peak amplitude to stimulate the membrane. The resultant force and length profiles can be seen in the live data window in the middle of the screen with force on the top and length on the bottom. Alternatively, the data files produced by this experiment can be seen on the right-hand side. As you can see, the profile changes for each subsequent frequency being executed. In this example, we are running a range of frequencies from 25 Hz to 250 Hz over a period of 5 seconds with a 10-second break between each stimulus. Subjects undergoing this type of stimuli can then answer questions about what they experienced, which can provide insight into cutaneous function and how it can be disrupted in diseased states. The final example we will look at is applying a constant load or pressure to investigate a nociceptor's receptive field. In this condition, you can vary the load, application area, velocity, and duration of stimulation while measuring receptor firing rate to map out its receptive field. It is important to remember that in this situation, we are controlling the applied load or pressure, and thus the system modifies the indentation distance required to reach the maximum load specified. Once this is achieved, force is maintained for a set duration and released. This can be repeated at the same load, or in this example, the applied force increases from 250 millinewtons all the way up to 400 millinewtons, with the resultant force and length profile shown once again on the right-hand side. With the 300C-I dual-mode indenter, you have a mechanical stimulator that produces precise, repeatable mechanical stimulation for a variety of nociception, somatosensory, or mechanosensory experiments. In addition, user variability is eliminated, and thus the need for multiple threshold tests. This is done by minimizing off-axis forces and delivering a constant application area over the full force range. Thank you for taking the time to watch today.